The one topic that you have in your syllabus is pressure belts and then planetary wind belts. Two of these topics. Now both of them are separated and they have to be separated essentially for the purpose of two different questions being asked from this topic. But the entire treatment of this topic is going to be done in two ways essentially. The first is that we'll go on to talk about pressure, and of course we'll go on to talk about the different type of pressure belts, but not confined to that. We'll go on to link the pressure belts with winds. That is, how is it that the different type of pressure belts going to determine the different type of winds. But then it will again not going to be completed from the perspective of atmospheric circulation. Atmospheric circulation will go on to take a different meaning altogether. So the topic is going to be overlapping and it is going to be interfering with two topics: atmospheric circulation as well as pressure, both of them. Picking up the first part, that is pressure, beginning with pressure, we'll go on to pick it up from the very basic level of it, because unless you go on to be having these very basics very clear, there is no way that a topic like that of climatology can ever be understood. Coming on to it. So we have changed the content of the topic and the nature of the topic. We're going to begin with first concept of pressure. Second, of course, some facts about pressure, that is terminology. Third is pressure laws. That's the third part. Fourth is the factors affecting pressure on Earth. And fifth will be associated with pressure and winds. Sixth will be associated with pressure and wind belt shift. Now, that is how the whole of the scheme of the chapter and the concept of it is going to be. Now, in general, pressure is defined as generally as or understood as the weight of the air above a column. That is the weight of the entire of the column of air above a certain thing. Now that is not exactly the case. You must go on to understand it in the most clear terms possible. That is this is a definition that, and this is a concept that is generally known to geographers. We are picking up what exactly is the concept and notion of it in some place like that of physics, because that is ultimately what will be more significant. The concept of pressure in this case is that is pressure is indeed, that is force per unit area. Now, force of what? And what exactly is unit? Any unit can be anything, but force of what? Now, imagine air molecules, they are not fixed. All of these air molecules in a air body, they are always going to be mobile, always going to be moving. Now, as they are moving, then they go on to keep on colliding as well. They keep on colliding with the ceiling, they go on to keep colliding with the board, they go on to keep on colliding with the ground. They're going to keep on colliding with my head, my hair, my lips, nose, everything, hand, everything. they keep on colliding. How much amount of collision goes on to take place, and in the process of this collision, how much amount of force is it that they go on to put in a per unit area is what is pressure. Now, take it from another angle. That is, imagine this whole of this classroom and that is filled with air, and they are going to be air molecules. Now, these air molecules are likened to like that of balls, tennis balls. These are going to be likened to that of tennis balls. All of these tennis balls, they keep on bouncing with each other, having collided with each other, and as they keep on bouncing with each other, in the process of bouncing with each other, they go on to collide with them, collide with the floor, collide with the ceiling, collide with your body, collide with every part of their body. The number of collisions of these balls per unit area is what is the pressure. In this case, we will going to convert these balls into molecules, and the force of the air molecules colliding with a wall, a ceiling, a floor, everything is what is called as pressure. So that is what we are going to be calling it as force per unit area. That's the name that is going to be given to it. So how much is it going to be the force per unit area? How much it can going to be? In general, what has been computed, as I say it, in general, what has been computed as the total amount of force per unit area is going to be equivalent to one of these unit is going to be 1013,200 dyne per square centimeter. That's one unit. Now, it has been converted to simplify it into 1013.2 millibars. Now, the same thing is going to be talked about in the form of 14.7 pounds per square inches. The same thing can be explained in another terms as well. That is, it is able to balance a mercury barometer to the tune of 29.92 inches or 760 millimeter. All of it is what is going to be at the sea level. This is going to be at the level of the sea. The highest of the pressure that is going to be achieved and that has been known is going to be 1084 millibar, and the lowest pressure has been 760 millibar. Now, both of these are subject to some degree of scrutinization because there is no way that in any book that you will go on to find them to be uniform. So, they will keep on varying to a certain extent. But by and large, that is what exactly that you can go on to know. Now, in this case, as you can go to say, we are talking about millibar. So, 1013.2 is going to be the normal pressure, and it goes on to be 760. That is going to be associated with the Pacific typhoon, a tropical cyclone. And 1084, that means something like some 70 units more than that. And low pressure is going to be not 70, it is going to be almost 300 units less than that. So, of course, low pressure goes on to become much more disastrous in this case. So, pressure is the force of air molecules per unit area. And where exactly is it that they are going to collide? That is, how much is going to be the force of air molecules that is colliding with it per unit area. That is the depiction of the normal pressure. Now, any area that goes on to have a pressure condition that is above 1013.2 millibar is going to be called by the name of high pressure or simply high. That is the way that it is going to be denoted. And any place that goes on to be having a pressure condition that is going to be lower than that 1013 is going to be called as low pressure, or it can go on to be simply called as low. Now, these are the type of symbols that goes on to be used for the purpose of denoting pressure conditions. It may happen that that is a high pressure, it goes on to be that between two high pressure zones. It is possible that between two high pressure zones, there will be area and this area will be called as trough. And then between two low pressure zones, there will be an area that will be called as a ridge. So whenever it is talked about, that is a trough of low pressure. It won't be called as a trough of high pressure, and then it will be called as a ridge of a high pressure, not exactly a ridge of low pressure. Terminology wise, that is what exactly it goes on to mean. These are going to be some of the basic facts associated with pressure, and we'll keep on using them for the purpose of exemplifying certain things. Now, to take it a bit forward, all of these high pressure and low pressure is going to be a pressure condition, and high pressure is always going to be associated with the air moving away from it, and a low pressure is always going to be one where the air will be moving towards it. It is going to be towards it, it is going to be towards it, it is going to be towards it, and this is how exactly it will go on to move in the northern hemisphere. So that is going to be a low pressure center. That is going to be called as a cyclonic circulation. From a perspective of circulation, it is going to be called by the name of cyclonic circulation, and that is going to be called by the name of anti-cyclonic circulation. Now, the basic reason behind calling it by the name of a circulation is because the movement of the winds towards it is not going to be taken in one dimension. That is, if the winds are going to move away, then they are going to be sinking, they are going to be subsiding, and that is the way that they can go to move also. So none of these things are going to be taken in any degree of isolation. That is going to be about facts about certain type of pressure conditions in this case. That's what we are talking about right now. And that is the type of terminology that we go on to be using. Now, that goes on to bring us into the third component, that is pressure laws. Now, there are going to be three laws that goes on to explain all of these. The first is going to be that goes to measure with pressure laws, Charles' law. Second is going to be Boyle's law. And the third is going to be Poisson's equation. Now, all of these laws, they go on to be talking about that it is a closed system. It is going to be closed. It's going to be a closed system. That means closed system means they're going to assume something to be constant. That means they're going to assume that there is something that is going to be constant, and then they allow other aspects to vary. So what exactly is it that Charles' law goes on to assume to be constant? That assumes that pressure is constant. Boyle's law goes on to assume that temperature is constant, and Poisson's equation goes on to assume that volume is constant. Now, Charles' law goes on to say if it is going to be constant, then Charles' law goes on to say that there are two of them that will go on to be variable, temperature and volume. So at any point of a time where the amount of temperature goes on to increase, there will be a commensurate increase in the volume. That means at constant pressure, temperature increase will go on to bring about an increase in volume. That is, the air will go on to rise. That's what will go on to happen. Boyle's law goes on to assume that the temperature is going to be constant. And if temperature is constant, then any increase in pressure will go on to bring about an increase in temperature. That will go on to bring about a decrease in volume. It will be associated with a decrease in volume. So the relationship in this case will be adverse. Any increase in pressure will go on to bring about any decrease in volume, and vice versa. Of course, this is also going to be vice versa. That is, any drop in temperature will go on to bring about a lowering of volume. Poisson's equation is going to be about interplay of, again in this case, that is going to be pressure, that is temperature and pressure. So any increase in temperature will bring about an increase in pressure. Now this is what exactly that requires to be understood much better. That is, as we said, that is, we said what exactly was pressure? Pressure was all about force per unit area. Force of what? Force of the air molecules, that is per unit area. Now when exactly is it that the force will go on to become very, very forceful, that will go on to become very high? Whenever there is an input of energy into it. I repeat, whenever there will be any amount of input of energy into it. So any input of energy will go on to cause it to be changing of sorts. Now, what we're going to say here is, that is, if we go on to increase the temperature, then temperature increase will go on to allow the molecules to vibrate. Temperature increase will go on to allow all of these molecules to become agitated, to become energetic. And as they go on to become agitated and as they go on to become energetic, the resultant effect in this case will be that that is, the force per unit area will go on to increase because they have gone to become agitated. The force per unit area will increase. And as the force per unit area goes on to increase, then the pressure will also increase. That means an increase in temperature will go on to bring about a rising level of molecular interaction, and this will go on to lead to an increase in the pressure. An increase in the pressure will go on to be changing a lot of things. So, or vice versa also. Now, most of the students in this case will be having a tendency to think that because the temperature goes on to rise, the pressure will go on to be lowered. But then it is only about what exactly is it that we have kept it as constant. It is these gas laws that actually go on to govern. It is these gas laws that actually go on to govern the entire of the factors that go on to affect the winds. So what are the factors that will go on to affect the winds is going to be guided by this pressure. And the factors affecting winds are going to be best seen on the Earth, on the planet, on the whole of the globe. So having discussed the concept of pressure, some of these facts and the pressure laws, that goes on to bring us on to the factors that affect pressure. The best way to understand this topic is going to be on the globe. We're going to pick up one quadrant of the Earth, that is 1/4 of the Earth, not exactly, that is the whole of the Earth. That will be, of course, there is something that will go on to show you with animation as well, in an animated version also. Now that is Earth. Of course, we can go on to make it complete. That is the way that the whole of the Earth can be made to be complete. This is the way. But we are going to be picking up only one quadrant of it. Beginning with equator. All in all, the temperature conditions at the equator happen to be high. Consequently, there is always a tendency for the air to rise. Now, assuming certain things to be constant, of course, in this case. So, the air will go on to rise from this place. This is where the air will go on to rise. Now, as the air goes on to rise, it goes on to hit the tropopause. That is going to be the tropopause. It cannot go on to rise beyond the tropopause at all. It has to be within tropopause. Now, this air is rising not only from here, it is rising from here as well, here as well, here as well, here as well, everywhere. Now, as this air goes on to rise, so what is the factor? That is, temperature is going to be one of the factors that goes on to allow it to rise. In this case, in the polar areas, it is temperature that will go on to allow the air to sink. This is the place where it will go on to sink. Because the temperature is very, very cold, the air has gone to become heavy, it has gone to become denser, and the tendency for it is to sink. Now, the air that rises, in this case, that goes on to strike the top of the tropopause and then go on to move in this direction. That is going to be moving in certain type of a direction. Of course, it goes on to move in both of these directions here as well as towards the southern hemisphere as well. Now, that is the air that has gone to become cold, and this is an air that is tempting to collapse. It's an air that is going to be tempting to fall, tempting to sink, tempting to subside in this case. And as it goes on to be tempted to sink and subside, it will go on to sink at this place. This is the place that it goes on to sink. And then as it goes on to sink in this place, of course, it will go on to complete its complete cycle. But the place where the air is going to be rising, this is what we go on to call as equatorial low pressure belt. That's the name that is going to be given to it, equatorial low pressure belt. So, equatorial low pressure belt exists because of temperature. It's temperature that is going to be the primary factor for leading it to become a low pressure region. Then that is going to be high pressure, polar high pressure. That is going to be the name given to it, polar high pressure. And that exists again because of temperature. Now, after falling into this place, the air goes on to move towards this region. That's the place where the air is going to be moving in this zone. The air will go on to move from this zone as well. This is another zone that the air will go on to move. Now, when this air goes on to move, both of them will go on to meet. And as both of them will go on to meet, this is going to be warmer, this is going to be cooler. The warmer air will go on to rise in this place. So, the place where they are going to rise, that will go on to lead to the formation of a subpolar low pressure belt. So, subpolar low pressure belt goes on to owe its origin to the air that goes on to rise. And this is a place that is going to be called by the name of subtropical high pressure. Now, that goes on to exist something about somewhere near close to about 40 degrees, 30 to 40 degrees. So, from a perspective of temperature, taking it as one of the factors, as one of these factors, that's what exactly that you tend to know. This is one thing that you happen to know in this region, only if you're going to take temperature into account. Now, there is a second factor that comes into interplay. That is, as the air goes on to rise, it goes on to become cooler, it goes on to become heavier, it has a tendency to sink, it goes on to sink. That's reason number one. For pressure to become high, there is another factor for which will go on to cause the pressure to be high. And that factor is that as the air goes on to sink in this place, in this region, then the sinking of the air in this region will be prompted by two factors also. One, of course, is going to be the rotation of the earth. There is a second factor that will go on to prompt its sinking and inducement of a high pressure in the region. And why is it that the high pressure will go on to evolve in this place? For what reason is it that is going to be evolving? it will going to come to this place. High pressure will be here, accentuated by the fact that at this place, the whole of this region is going to be having a very large radius here. And at this place, the radius is shrinking. The radius is shrinking. So that much amount of air finds itself compressed into a small amount of space. That means the space that is going to be here is getting constricted and it is prompted to shrink itself into this region. That's where it goes on to shrink. Because it goes on to shrink itself into a lesser amount of an area, consequently, the pressure goes on to become high. The force per unit area in this case goes on to become high. That is another part associated with it. Another part associated with it. So that goes on to make it subtropical high pressure belt. Then, going to pick it up, why is it that the subpolar low pressure belt goes on to evolve in this place? There are going to be two factors associated with it. One of these factors in this case is that is, of course, the air, so there is the air coming from the subtropical high and the polar high, both of them going to meet, and one of this air, particularly the warmer air, goes on to rise. So because the air goes on to rise, it will go on to induce a low pressure condition beneath. So that is why the low pressure condition goes on to evolve in this place. Second is, all of this air that has come from the subpolar region, it has come to a place where the radius has gone to increase. That is, this air that has been constricted in such a space, it has come to a place where the space is very, very large. In this case, the space has gone to shrink. In this case, the space is going to be very large. Consequently, this air will have a tendency to rise, expand, and then go on to rise. Now, as this air goes on to rise, this also air is, the air here also goes on to rise. Now, this will go on to lead to formation of a complete cell. That is how exactly that will go on to move. That goes on to make a complete cell of itself in this case. And the air that goes on to rise here, that also goes on to make a complete cell of itself here. So that is the way that they start moving. And of course, the air that goes on to sink here, one of these branches goes on to go towards the polar regions, another will go on to come towards the equator. This is the place that will go on to come to. That will go on to make another cell in this case. Now understand, the equatorial low pressure belt owes its origin to two factors. The first is temperature. The second is rotation. The subtropical low pressure belt goes on to owe its origin to two factors. The first is sinking of the air. The second is a decreasing radius. The subpolar low pressure belt goes on to owe its origin to, again, two factors. One of is a increased radius. The second is upliftment. The polar high pressure belt goes on to owe its origin to temperature. Now this leads to the evolution of the four pressure belts: equatorial low pressure belt, subtropical high pressure belt, subpolar low pressure belt, and high pressure belt. So in this case, of course, it is going to be temperature as well as rotation of the Earth, two of these factors. Now this leads to the evolution of what we go on to call it as pressure belts. And the pressure belts go on to comprise of equatorial low pressure belt, subtropical high pressure belt, subpolar low pressure belt, and the polar high. Now, while this type of pressure belts go on to evolve, they also go on to lead to the evolution of wind belts. Now, imagine this is the wind that is going to be moving from the subpolar, from the subtropical region to the equatorial region. These are the winds that are going to be moving at the surface. And then another wind goes on to be moving at the surface here also. And then there is going to be another wind that is moving here as well. Now, these are the three winds that happen to be moving in this region. Now, when we go on to be talking about the movement of the winds in such a manner, all these winds that go on to move, this is the way that will go on to move. Of course, they cannot go on to move in a straight line for a simple reason. That is, on a rotating body, nothing can go on to move in a straight line, and they will go on to get deflected towards their right hand side because of the Coriolis force. So all of these winds will go on to get themselves deflected from the subtropical high pressure belt to equatorial low pressure belt. Now, before we go on to pick up this part, there is going to be another aspect. There is the co-relationship between pressure and winds. Now, we talked about two concepts of pressure. One of them was going to be a high, another was going to be a low. That was going to be another one. Now, both of them are going to be surrounded by isobars. They are going to be surrounded by isobars. And the value of these isobars keep on decreasing. So, the air will going to have a tendency to move towards the lower values. That is, it will always going to move from high to low. High pressure to low pressure, it will going to move towards lower values. Now, in this case, the gradient that goes on to exist in this, around high pressure, the gradient is always low. Now, this gradient is going to be called by the name of pressure gradient. It is going to be always low. In this case, consequently, the wind speed around high is going to be low. That is, anticyclones are not going to be having a very high wind speed. Then, picking up the pressure gradient, that is the pressure gradient force, a low pressure is going to be surrounded by many closed isobars. Many closed isobars in this case. That's how exactly the low pressure is going to be surrounded. Now, the pressure gradient in this case is going to be very high. That means the winds that go on to move towards it, because they're going to move from towards a very steep pressure gradient, these winds, that is the way that they can go on to move into this region. This is the way that they can go on to move into this region. These winds are going to be having a very high speed. So, winds always go on to move with a high speed around a low pressure. And the pressure can go on to be as low as we have talked about, that is even some 300 millibars lower than the normal, while the highest pressure can go on to a maximum 60-70 millibars higher than the normal. So, pressure, that winds will always have a tendency to move from high pressure to low pressure. They will always going to have such type of tendency. And in trying to move towards a low pressure, they are going to be deflected towards their right because of the Coriolis force. So, around a low, they will go on to get deflected towards their right hand side. They will go on to get deflected towards their right hand side. They will go on to get deflected towards the right hand side, and so on. This is the way. Consequently, this is how the cyclonic circulation goes on to move. This is the way that the cyclonic circulation goes on to move in the northern hemisphere. That's the way that the cyclonic circulation goes on to move in a northern hemisphere. Now, we'll go on to apply this concept in this case here. So, the winds will go on to move from, that is the co-relationship between pressure and winds. So, winds will go on to move from subtropical high pressure to subpolar low pressure. And in doing so, they will go on to turn towards their right. That's how they go on to turn towards. They go on to turn towards their right hand side, towards their right hand side. Now, this is what we're going to be calling it. These winds are going to be called by the name of trade winds. Now, trade winds means it doesn't going to lead to trade of sorts. Don't go to understand it. Trade is a German word which conveys the meaning that is, these winds are steady. They move with a steady velocity. They move in a steady direction. That is, both of these things are steady. Steady direction as well as steady speed. Both of them, speed and direction, both of them are speedy, and consequently they are going to be called by the name of trade winds. Similarly, all of these winds are going to move from subtropical high pressure to subpolar low pressure. That is the path that they're going to take. This is the type of a path that they're going to take. And these are the winds that are going to be called by the name of westerlies. These are the winds that are going to be called by this name, westerlies. When these winds are going to be called by the name of westerlies, of course, they're going to move from west to east in general. That is the dominant movement. So that is going to be the westerly belt. This is going to be the westerly belt. This is going to be the trade wind belt. That's the trade wind belt. That is from high pressure to low pressure. Again, in this case, the movement will going to take place from high pressure to low pressure. This is the way that the movement will going to take place. Now, these are going to be called as polar easterlies. Now, in this case, as you will going to find it, that is the subpolar low pressure belt goes on to be a convergence zone. Subpolar low pressure belt is a convergence zone, and so is the equatorial low pressure belt. That is also going to be a convergence zone of the air that is going to be coming from these directions, that is from the southern hemisphere. This is an area that is going to be also called, because of it, as the intertropical convergence zone. That's an area that is going to be called as ITCZ, Intertropical Convergence Zone. That's the name that is going to be given to it, Intertropical Convergence Zone in this place. And that is also going to be convergence zone. Now, both this is a place that is it will be essentially known for certain type of cyclone formation. This is the place that will be known for cyclone formation. So all the temperate cyclones happen to affect the region because it's a low pressure zone. Now, this is also a low pressure zone, but cyclones don't going to come into this region because it lies on the equator. It lies on the equator, and on equator the Coriolis force is 0, and that's the reason cyclones don't going to come to this place. Now, this is something that is going to be talked about subsequently in atmospheric circulation. Now, understand this part. Now, with the trade winds coming and joining together, and then these trade winds have come, they have converged here, and as they have converged, they're going to rise. As they're going to rise, they're going to get cooled, they're going to move, and then they're going to again sink. That goes on to form a complete cell. This is a complete cell. It is this cell that we're going to be calling it by the name of Hadley, and it is thermal cell. It's a thermal cell, Hadley cell, after the name of a scientist who found this cell. It's a Hadley cell that is going to be called as a thermal cell. And then this is one that has been found by Farrell. It's not thermal. It's going to be non-thermal. That is going to be another one that is going to be called by the name of polar cell. And it's again thermal because it is driven by temperature. This is the main driving force that is driven by temperature. That is, the air sinks and subsides, it goes on to move, and then that is how exactly it is going to be driven. So what all happens in this case is that that is going to be a Hadley cell, it's going to be a cell. This is going to be another cell, Farrell cell. Then there is going to be another cell that is going to be a polar cell. And then in between, you're going to be having trade winds, westerlies and polar easterlies. This is the type of relationship that we're going to think of. So these are the three wind belts that we have: trade wind belt, westerlies, and easterlies, polar easterlies of sorts. This is how we can go on to complete that part, polar easterlies. Now, that is going to be the general relationship that goes on to exist between temperature, pressure, and winds. And it's one of these generalized pictures that happens to evolve in this place. So all in all, that is what we talked about have been, what is the concept of pressure, what are the facts about its pressure, terminologies, pressure laws, that is gas laws that we're going to be talking about. There is Charles' law, Boyle's law, Poisson's equation, the factors affecting it, and on the earth, and what exactly is the pressure affecting it, and what is the relationship between pressure and winds, and pressure and wind belts. That is all that we have discussed in this case. Now you will going to find that there are going to be two different type of circulations. One is going to be on the surface, that is going to be surface circulation. Another is going to be upper air circulation. All of these circulations go on to be part of upper air circulations, all of it upper. So there are going to be two type of circulations in a cell. In this cell, that is how exactly that it keeps on moving. There are going to be two types of circulation. One is on the surface, another is going to be upper air. One is surface and upper air. Surface and upper air. That's the way that the movement takes place. Now, the whole of these things can be shown to you in a three-dimensional manner in an animation. Now, we are talking about this animated part of it, and we're going to begin with talking about the idealized Hadley cell circulation. Now, as you can go to see it, this is how the Hadley cell circulation takes place. The air rises from the equator, sinks at the subtropics, moves back towards the equator. Now, that is where it goes on to lead to clouds. The whole of this region is going to be clouded. That is in 3 dimension, and this is going to be in a profile. The whole of the world map is going to be in plan. Now, these are warm air masses. These are going to be warm, that's going to be warm air, and that goes on to move. That goes on to become cooler. And as it goes on to become cooler, it goes on to become warmer once again in the process of cooling. Red means warmer, and blue is going to be cooler here. So that's going to be red is warmer and blue goes on to be cooler here. Now that is going to be Hadley cell. This is going to be one cell, and that is Hadley cell. The second of it is going to be the tropical and the middle latitude components. Now, this is one wind that we're going to be calling it by the name of trade winds. These are going to be called by the name of northeast trade winds. Here it is going to be called by the name of southeast trade winds. And both of them going to converge here. And that is what we're going to be calling it by the name of ITCZ, or the Intertropical Convergence Zone. That's the name that is going to be given to it. In all of these zones, there are going to be some pockets of high pressure anticyclonic circulations. And winds from this place find their way to low pressure zones. From here, they're going to find their way towards the northern hemisphere as well. This is what they're going to be called by the name of westerlies. And take a look at it. These winds are going to be red in color. That means they are warmer. So that is going to be here as well. That's going to be again another westerly. And these winds are going to turn towards, that is, they have turned towards their right because of the Coriolis force. They have also turned towards their right because of the Coriolis force. And in the southern hemisphere, they have turned towards the left because of the Coriolis force. That is going to be tropical and middle latitude components. Then there is another of this component that is going to be added, that is high latitude component. Now that comes into being here. There is the winds that go on to move from the high pressure or polar areas. They come, and both of them go on to converge in this place, all along this zone that they go on to converge. This is the convergence zone, and when they are going to converge, one of these winds go on to rise, and when one of these winds go on to rise, that goes on to lead to the formation of low pressure in this zone, in this area. That goes on to be high pressure. There is a high latitude component, and that is where all the winds, warm winds, these are cool winds, very cold winds. The winds that go on to be coming from the high pressure region of the polar regions, they also go on to turn towards their right. And in this case, they're going to be turning towards their left. That's the way that they're going to turn. Now, in this way that they're going to form Hadley cell, then the cell that is going to be here is going to be Ferrel cell, and then you have a polar cell here. These are the 3 cells that we showed you. Now, that goes on to make it a very good component of it. Now, a slight amount, and of course, we go on to be talking about the pressure zones. That is a low pressure, this is going to be a high pressure, this is again going to be a low pressure, this is again going to be high pressure. So, there are going to be 4 pressure belts: equatorial low pressure, subtropical high, subpolar low, and polar high. And accordingly, there are going to be 3 wind belts. There is the trade wind, the westerlies, and the polar easterlies. Now, over and above, we can go on to insert one part that is, of course, not part of it, but for you to imagine it in a better manner, there is upper atmospheric flow. Now, this will go on to imply some jet streams, but you need to know just a brief about what exactly are jet streams so that we can go to pick up the topic in the next section of sorts. Now that is what we have talked about. Now this is how the Hadley cell circulation is, and there are going to be two belts of jet streams that go on to move. These are the jet streams that go on to move at a very, very high speed. That is, the speed with which these jet streams go on to move is going to be close to that of something like 240, 300 kilometers an hour. There are going to be two such type of belts where the jet stream can go on to move. One is going to be the polar front jet stream, another is going to be, that is the subtropical westerly jet stream. Both of them going to move from west to east. So there is going to be symmetrical pattern found here as well. There is going to be one jet stream here and another that is going to be in these zones. Of course, they are not only going to be only two types of jet streams. Now that is the overall circulation of atmosphere, and you can go on to find that is here in this place. That is the air that goes on to rise. This air that goes on to rise, the air that goes on to rise here, that is the air that goes on to turn towards its right hand side on the upper part of it. This is going to be part of upper air circulation that goes on to turn towards its right hand side, and this is what exactly goes on to form the jet streams. Now this is one part that we are going to be discussing about when we are going to talk about atmospheric circulation. But that's the way that the movement is taking place here. Now this is all about what we have talked about, that is pressure and winds. We can go on to put these labels off, and then you can go on to see in a much more clearer manner as well what exactly and how exactly it is that this circulation takes place. We can always go on to put the labels on with the Tropic of Cancer, North Pole and what not, that you can go on to find it here. This is all about the pressure, causes of pressure differences, the pressure belts, how many winds are going to be there, and a small manifestation of these winds in the form of a jet stream, which is going to be talked about more when we are going to talk about atmospheric circulation. So far what we have talked about is what exactly is pressure, how is it that the pressure factors affecting pressure are going to determine, what are the gas laws, how is it that different type of pressure patterns go on to evolve, and how is it that there is any type of a distribution on the map of the world. We went on to show you with the help of an animation, with the help of a three-dimensional diagram, so as to make things easy for you. Now we go on to pick up the second case associated with it. That is, how is it that the pressure belts go on to shift? Of course, with the thermal shifting of equator. Now understand this word, thermal shifting of equator. Thermal shifting of equator is the shift of equator from 22nd of March and 23rd of September position towards either northern hemisphere, either on the Tropic of Cancer or on the Tropic of Capricorn. So on 21st of June, the sun is shining vertically on the Tropic of Cancer, and that effectively transcends itself into a pseudo equator. It is equator, but that is called as thermal equator. The concept of equator is a manifold. The one concept with which the students at a school level 6-7 standards happen to know this is that it is one of those lines that divides the world into two hemispheres. But of course, at the civil services level, this is a definition that is always going to be fraught with some type of danger. And when we are going to say that is going to be fraught with some type of a danger, then that effectively goes on to mean that the concept of equator doesn't go on to function so much. And why is it that it doesn't go on to function is because of many factors. That is, it's not the half of the world that goes on to get divided along it. Consequently, we go on to call that region where the sun is shining vertically as the thermal equator. So when the thermal equator goes on to make a shift, then the pressure belts also go on to shift. As you can go on to see it and as you can go on to observe this part, this is what exactly it goes on to show. Now, you can go on to take a look at this. All of this low is going to be low pressure belt, and all of these that is high will be high pressure zones. These are the two zones that we are talking about. Now, while talking about it, you're also going to understand two other concepts. That is, the first is in this case going to be associated with the low pressure belt, that is equatorial low pressure belt. That's one. That is going to be 5 degree north and south. That's the place that is going to be placed 5 degree north and south. And then thereafter, it is the winds that go on to rise at the equator and then they go on to fall. That is the place where they go on to fall, that is going to be the subtropical high pressure belt. Both the places. That's how it is going to be. That is the place where they go on to fall that goes on to form the subtropical high pressure belt. Now, this is something that is coming written for you as well. So, we have two of these belts, equatorial low pressure belt, subtropical high pressure belt, and you're going to take a look at these winds, that is cool winds. As they're going to descend down, they're going to become warmer and then they're going to rise. Now, that is going to be between 30 to 40 degree north and south, both of them, in both of these cases. Now, the third one is going to be beyond that. That is going to be the part of the Ferrel cell. This is going to be the Hadley cell. This is going to be the Ferrel cell in this case. So, these are the westerlies. These are the westerlies which are going to move towards it, and then they're going to come back in the form of a return flow of sorts. And they go on to fill this subpolar low pressure belt. Now, while the Earth goes on to rotate, these winds also go on to keep on making a movement. And the third zone, of course, is going to be the polar cell. That is, these are the polar easterlies. All of these winds are going to be called by the name of polar easterlies. So, all in all, that is you have a polar high pressure belt from where the winds go on to move, and this is how exactly the pressure belts go on to be present. That is, in this case, the polar high pressure belt is very well developed of sorts. Now, as you go on to move further, pressure belts, as we talked about, they are going to be caused by the differences in the temperature, and that is going to be caused by the position of the Earth around the Sun. This is Sun, and how is it that the Earth goes on to revolve around it? That goes on to determine what will be the temperature condition. And this is the idealized distribution of pressure on the Earth. And that is tilted, of course, at a 23.5 degree towards the Sun. On account of this inclination, there are differences in heating of the continents, oceans, and all of them. And these differences are both, of course, going to be in July and in January. Now, that is something that is going to be understood. January and July represents the representative conditions of that region, whether they're going to be in the northern region or going to be in the southern region. That's the southern hemisphere part. And that is where we're going to be talking about. It's going to be the northern portion of it, the tropic of Cancer, and that is where the sun starts shining now. Now, when the sun is overhead, as you can go on to take a look at it, that is here. If we roll back, January and July are the two of these situations. They represent the winter and the summer seasons respectively. Now we are going to pick up the one case when the sun is overhead on the Tropic of Cancer. That is where it is going to be, Tropic of Cancer. The pressure belt has shifted towards north, and just going to take a look at this pressure belt that is another of this look. Now that's the condition that we are going to be talking about. The whole of the pressure belt has shifted itself northward because the sun is shining vertically on the Tropic of Cancer. So just going to take a look at it, that it has shifted northward, and that the polar high pressure belt is feebly, meagerly, in a very meager manner it is going to be developed. While in contrast, the polar high pressure belt in Antarctic, in the southern hemisphere, that is very, very well developed in this place. It's pretty well developed, as you can go to see it downwards. That is, its area is going to be much more extensive than what it is going to be with respect to the polar high pressure belt. Then, moving forward, as you're going to find it, when the sun is going to be shining vertically on the Tropic of Capricorn. Now here the sun has shifted southward. This sun has shifted southward, and once you're going to take a look at it, that's where you're going to take a look at it. That is, this is the subpolar low pressure belt, and the polar high pressure belt in this case has been feebly developed, while the polar high pressure belt in the northern hemisphere is very, very well developed. This is largely on account of the fact that the sun has shifted southward. Now you can go on to take a look at it somewhat once again. In this case, that is, how is it that it goes on to shift northward and southward. This is going to be January, and the winters are going to be in the southern hemisphere at that point of a time. So when the sun is shining vertically on the Tropic of Cancer, just take a look. The whole of this pressure belt has shifted northward. The whole of this pressure belt has shifted northward. Now, in contrast, when the sun is going to be shining southward, that is, the whole of it has shifted southward, that is on Capricorn. Now, that is how the pressure belts goes on to shift, and accordingly, the whole of the wind belts also go on to shift. We're going to talk about the wind belts also go on to shift in such a manner. Now, accordingly, just going to take a look at it along this region. In the summer season, the Mediterranean region going to be coming under the influence of the desert, while in the winters, they go on to be coming under the influence of the rains. That is, the best manifestation of such type of a shift is going to be found in these conditions. That's where exactly it is going to be found, in the Mediterranean regions. And Mediterranean regions are the best manifestation of it. You can go on to take a look once again in this case. That is, this is where the westerlies are. They have shifted northward because of the shift of the sun southward, and the whole of this region has come under the influence of the westerlies. You take a look once again in this case. That's what we are talking about. That is, this is the shifting of the pressure belts causes seasonal change in climate in both of the places. Now we are going to be talking about that's the normal condition. That's the normal condition. Now that is when it is the whole of the region is going to be hot. Now when the whole of the pressure belts go on to shift northward, what exactly is likely to shift southward? Then the entire of this zone goes on to come under the influence of the westerlies. The whole of this zone comes under the influence of the westerlies. So accordingly, what happens is that this region starts receiving winter rains, while in the summer they are going to be under the influence of the trade winds, the dry trade winds. And that is the basic reason that such type of a condition as is found to be associated with the Mediterranean regions are going to be found. And when we are going to be talking about when the sun shines vertically over the equator on 21st of March and 23rd of September, the pressure belts remain balanced in both the cases and both the conditions. What we talked about was how is it that the pressure belts go on to shift, and what are the implications of the shift of this pressure belt. The shift is going to be taking place, and that has been shown to you in an animated form. Now, the greatest impact of such type of a shift takes place in the Mediterranean region, which comes under the influence of the dry trade winds in the summer and they come under the influence of the westerlies during the winter season. So they're going to be having winter rains and they're going to be having a summer drought type of a situation.